Hey y'all, hope you are doing well today. And for those of you who are virtually learning today, this is kind of some heavier, meatier stuff a little bit. And if you can get through this stuff, if you can do these types of problems, you can do anything we got all year long. So what we're doing is we're just kind of repurposing some of our previous ideas for the more complicated situation of launching a projectile at an angle. Right now we've limited ourselves to launching projectiles horizontally. Now we're going to launch projectiles at an angle. So that's going to complicate things a little bit, but I think now that we have a little bit of background, we should be able to make some headway here. So one thing to recognize is that if I launch a projectile at an angle, that my x and y components of motion are still going to be independent of one another. Okay, one does not affect the other. So if I have a situation where I've got those old toolbox equations, I can still utilize those toolbox equations. Okay, so before we even start thinking about stuff is that with horizontal motion we said that my velocity in the x direction was constant. Okay, but now all we have to do is realize that if we launch something at an angle here, that my x component of velocity is just the adjacent leg of this hypotenuse. And so that my velocity in the x direction is going to be whatever my velocity is at this angle times the cosine of theta. That's going to be constant. So throughout my entire journey, no matter what this projectile does in its path, so let's say this projectile goes like so, okay, this velocity vector right here is going to be constant throughout. So if it's traveling at 5 meters per second here to the east, it's traveling at 5 meters per second here to the east, okay, all the way along. Okay, so what we're going to do now is we're going to give you about a bunch of new toolbox equations, but really they're the same equation. They're just incorporating a little bit of trigonometry into it. So before we said that our displacement, our delta x here, equals velocity times time. Now all we have to do is say that our x component, our delta x here, our displacement in the x direction, is now my velocity times the cosine of theta times time. I just have to realize that it's not this velocity, it's this velocity that's going to be constant. Okay, it might start at this velocity, but this velocity, that x component, is going to be constant. So this right here, guys, is a new toolbox equation. Delta x equals VO cosine theta t. Now, we can also rearrange our old equation for velocity in the y direction. Okay, because what's going to happen in the y direction is now my velocity component in the y direction is this, okay, and so my initial y velocity is v sub 0 sine theta. But because the y component of velocity undergoes an acceleration, we said before that my final velocity in the y direction equals vi plus at. Guess what? Where a is the acceleration due to gravity, so you could say gt. But now we've got to say VO sine theta plus AT. New toolbox equation. It's really the same one. We're just incorporating this idea, that sine of theta, because it's this opposite leg of this hypotenuse that's going to be that vector component. We had an initial equation which said delta y equals VI t plus 1/2 AT squared. Now all we do is say it's VI sine theta t plus 1/2 AT squared. Box that up. That's a new toolbox equation. And then this one's probably the most complicated one. Before we said VF squared equals V sub O squared plus 2A delta x or 2A delta y. Now we just plug in this sine theta squared. Okay, VO sine theta, square this whole puppy. That's all you got to do. Other than that, all those old toolbox equations still apply. We just need to incorporate that angle into it. Okay. So, a couple things to kind of bear in mind here which kind of illustrate this idea. Let's say I'm a passenger in a post-COVID world airplane and I decide to throw a ball up in the air. Okay. Now, all other things being equal, okay, you might wonder, like, why doesn't it happen when I throw this ball up, it immediately go back and hit a passenger in the eye back here? Well, that's because it has a horizontal component of velocity and a vertical component of velocity, okay? Because you are in this reference frame where you are traveling with the plane. So for you, you'd throw this ball, it'd go straight up and straight down. For an observer outside the airplane, it would look like it would have this type of motion. It would have a parabolic motion as it traveled through the air this way. So it's really no different than a projectile launched at an angle. And that's a good thing, because if you ever dropped a fork while eating, it would go back and stab somebody behind you. So that's probably a good thing. Now, when you do launch projectiles at an angle, a 45-degree angle is going to yield the greatest displacement in the x direction as long as your delta y is 0. And that's because it has a perfect marriage between your x component of velocity and your y component of velocity. You want the ball to stay as long in the air as possible while still maintaining a greater distance as possible. You need that x component to be as strong as possible. Now, what's really interesting is that if I have angles that add up to 90, they will travel the same distance. So these complementary angles, if I, at least in a world without air resistance, if I shoot something at a 30-degree angle versus 60-degree angle, they will travel the same distance in the x direction. If I launch something at a 15-degree angle and a 75-degree angle, they will travel the same distance in the x direction as long as they were given the same initial velocity and as long as there's no air resistance. Okay? One benefits from having a greater delta x but less time. One benefits from more time but less of an x. So complementary angles actually end up going the same displacement in the x direction. Okay? Now, there are a couple curious things that happen as a result of this idea of projectiles launched at an angle. Let's say you are a hunter down here, and you decide that you, in a post-PETA world, you decide to hunt monkeys for a living, and you've got a monkey hanging from a tree branch right here. We'll kind of make this tree up this way. It's kind of maybe winter. It's lost its leaves. And at immediately the time that you shoot at this monkey, the monkey recognizes this and drops from the tree. Now, you've got a rather slow-moving bullet, okay? And so the bullet falls appreciably in between the time that the monkey falls and this bullet reaches this monkey. But what is curious is that as long as you aimed at this monkey initially, and as long as you shot at exactly the same time as the monkey drops, you will hit this monkey every single time as long as your velocity is enough to cover this distance before the monkey reaches the ground. And if you wonder why that is, just think about the fact that this monkey is going to be accelerated due to gravity, okay, at the same rate that this object is accelerated due to gravity. So by the time this object travels this distance, this will have accelerated or it will have descended at the same amount that this monkey has fallen. And if you don't believe me, there's a video that's attached to this lesson today that shows how this is done. And it doesn't matter what velocity you use, that monkey and this bullet will fall the same distance. Another curious feature is this. Imagine you are living in some medieval world and you're kind of storming the castle, and you see a person up at the top of the castle who's hurling insults down upon you, and you don't take too kindly to it, and so you decide to throw something at that individual. But you're not very strong, so you're not going to get there. And this individual also, he hurled an insult at you for a reason. He doesn't like you. So he throws something at you, and he also is somewhat feeble armed, and he doesn't get there either. But what is interesting about this is that if these two people aimed correctly and threw at exactly the same time, these two objects will strike each other in their path, because this will fall the same amount that this object will fall. Okay? and as a result, that object would collide. So I'm going to stop the video here. I want you to watch a short YouTube video called Shoot the Monkey. It's run by people at MIT. And then I'm going to have you watch how I do a demonstration problem with these new equations.